All right, I think we're recording. So today we're going to get started with chapter 4. Chapter 4 is about extending past basically quadratics into polynomial functions. There are a bunch of different sections in this chapter. We're not going to cover all the material in each one. So this one we're going to be talking about, actually here, let's just pull this up. We're going to be talking about more nonlinear functions and graphs. Specifically in this chapter, we'll be talking about the graphs of polynomial functions, which I will explain shortly. So polynomial functions and graphs. These are two different graphs of polynomial functions. And you're going to notice some interesting things about these. So obviously a quadratic we've looked at looks like this or like this. Then we've looked at linear equations, which look like this or like this or like, well, this wouldn't be a function, but you know, they can look straight up and down. Basically, we've looked at straight lines and we've looked at curves with one little dip in them. And now we're going to start looking at things that look a little bit crazier and weirder. You can do a lot of different math with these things, but most of the math we're going to do is actually going to be relatively easy compared to like solving quadratics and things like that. So don't get too panicked just looking at the graphs. Some key terms, I would strongly recommend writing these down. These definitions are going to be very useful, both going through your homework and to have on the test. And of course, you do get your notes, so this is probably worth copying. You can always pause the video if you need more time to copy it once I get the definitions up here. But the first one are local maxima or minima. These are also often or occasionally called, oh, what's the other word for it? There's another word for it, I can't remember it off the top of my head. But a local maximum or minimum occurs when a graph changes from increasing to decreasing, which is a local maximum, or decreasing to increasing. That's the local minimum. A graph can have unlimited local maxima and minima. It's actually dependent on something we'll talk about in a little bit. But let's go back and look at these. So for instance, this, where's my pen? There it is. Sorry. This right here, this is a spot where this graph goes from increasing to decreasing. So this is a local maxima. It's the maximum point that this hits locally, right? So all the points to the left and to the right of it, at least for a little bit, are smaller. This right here is a local minima. This is a local minima. This is a local minima. This is a local maxima, right? This one's the highest point that's nearby it. This one's the lowest point that's nearby it. Depending on how this graph looks, so if you zoomed in really far on this and it looked like maybe something just barely like that, then you'd also have a local max or minima here and a local maxima here. This one looks like it gets pretty straight towards the end there, so I don't know for sure whether or not that's switching the slope. But anyway, so that's local minima and maxima. And then absolute maximum and minimum are the point at which the graph hits the highest, the maximum, or the lowest minimum point. There is at most one absolute minimum or maximum on a graph. So if you look at these ones actually don't have, this one has an absolute minimum. And while there are two different points that hit the absolute minimum itself is a one value. These are going to be at about the same spot. Actually, for this graph, they should be at exactly the same spot. So there's only one absolute minimum. For this graph, the absolute maximum is infinity because presumably that's going to keep going up forever. And the absolute minimum of this one is also presumably negative infinity because that one's going to keep going on forever. So these ones aren't the best examples. We'll look at a couple other ones later that do actually have absolute maxima and minima. And those of you, actually all of you, should be at least somewhat familiar with the sine function. Looks like this. So they've got an absolute maximum here and an absolute minimum here. And so there can be multiple points that hit the absolute maxima or minima. So I realize that the wording of that definition is a little bit weird, but the actual value itself, there's only one absolute minimum or one absolute maximum. Okay, so identifying maxima and minima. I kind of already talked about these graphs, but this is just reviewing them a little bit. So right here we have a local minima. Right here we have a local maxima. Our absolute maximum is way up there. Our absolute minimum was way down there. For this one, the absolute maximum is infinity. Absolute maximum is infinity. There's a local maximum right here. And then there's local minima at this spot and at this spot. They both also happen to hit the point that is the absolute minimum, which is somewhere down in like the negative 25 range. I'm not exactly sure. And I don't really care that much. Point is, it's those. For these ones, these are a little bit more complicated. So we've got this graph right here has a local minima right here. It has a local minimum right here. It has a local maximum right here and a local maximum right here. So these are pretty easy to find, right? And we could identify points on these two. This one doesn't look like it's really close to a point, which is unfortunate. Maybe -1/2, -7.5, something like that. If you are asked to identify these on like a homework question or on a test question, it's probably hopefully going to give you actual points. This one, I'm going to pretend it's right in this corner. So, that one could be at like 2, 5. The minimum here could be at like 3, 2 if the graph wasn't terrible. This one actually looks like it almost does hit a point. So it's like what, maybe 5, 6. So you'd have these two are maxima. And then these two are minima. Now, interestingly, you actually can have a local minimum that's higher than a local maximum. So it's not the case in any of these graphs, but let's say you had a graph that looks something like this. So here's, oh wow, that was terrible. Here's our coordinate plane. So you had a graph that looked like this, and then it came to here, and then it dropped here, and then it went here, and then it went like this. So you'd have a local maximum right here and a local minimum right here. And this local minimum is actually higher than this local maximum. So local maxima and minima is really just whether or not, if you see this dip, that's a local minima. And if you see the upward one, then it's a local maxima. So on this one, for instance, we have a local maxima right here. There might be one in here. It's hard to tell. It doesn't look like this line actually ever switches, whether it's going up or down. It's kind of always just barely going up. So we're not sure right there. It's got a local minima right here, local maxima right here, local minima right here. And then the absolute maximum is infinity. The absolute minimum is -infinity. Let's say, for instance, though, that this graph stopped right here. So we can ignore all of this stuff. Ignore. And then let's say it stopped like right here. So we could ignore all of this stuff too. So let's say we just had this graph right here. This would be our absolute minimum. It's the lowest possible value. And this one right here would be our absolute maximum because it'd be the highest possible value. And I think your test question or your homework questions are going to be a lot more likely to not have the lines going all the way in both directions, just because it'll make it a little bit more simple. This one, for instance, has a local maxima on one and a local minima on the other, or an absolute maximum on one and an absolute minimum on the other. So again, local maxima and minima, those are easy. Just every time you see a dip, this one has a local maximum, and then a local minimum right here. This one also has an absolute maximum, and that's right here. All right, this is the highest point this graph will ever get to, whatever this y value would be. This one only has one maxima or minima, and it's right there. It's an absolute minimum. It's right at the bottom. The absolute maximum is, of course, positive infinity, because both of these will presumably go on until infinity. So this one just has the one max or minimum right there. Now, one thing I do want to say before I move on from this is that absolute maximums and minimums are local maximums and minimums, right? So this is the absolute maximum of this function. It's also a local maximum, right? Because it is the highest point nearby. This is the absolute minimum, but it's also a local minimum, right? There's nothing nearby that's going to be lower. So it is both an absolute and a local maxima, or maxima in this case and minimum in this case. Absolute maxima and minima are always local maxima and minima, but the same is not true the other way. This is a local maxima, but it is not the highest possible point. This is a local minima, but it is not the lowest possible point. So neither one is absolute. Hopefully that makes more sense than it sounds like it is right now. So let's look a little bit at what polynomial functions look like symbolically. Polynomial functions are basically the expanded form of what we've already seen in functions. So we started with linear functions, then we moved to quadratic functions. That looked like this. We went from this mx plus b to ax squared plus bx plus c. This we can think of as having an exponent of 1. This is having an exponent of 1. So really what we did was we just added another term to this that had an x squared, right? a quadratic function is just a linear function with something x squared attached to it. Polynomial functions basically just take this further. So we keep adding on another exponent to x. So like we go up to like x cubed plus x squared plus x plus 3. And then, you could go x fourth plus x cubed plus x, and so on and so forth. And that's what polynomial functions are. So the general formula for these is a sub n x to the n, a sub n minus 1, x to the n minus 1, all the way down until you hit ax squared and then ax and then just a. So the a sub whatevers are just constants, they're just numbers. But instead of choosing letters for them like we do with quadratics and stuff, because we don't know how many there would be, right? You could have x to the 137th. And if you had every other function here, you'd have 137 values in front of x, whatever these are. So we don't know what this value is, right? There are not that many letters, so we just use a sub n here instead. And you can kind of ignore the n's. Just know that these are constants. But there are some important things to get from this formula, and we'll talk about those right here. So the first a value, or the number in front of the x with the highest exponent, is the leading coefficient. So for instance, if I have, actually we'll look at an example in a little bit on this slide. The highest exponent itself, so whatever the x to the highest number is, let's say this is 20. That's really bad. Let's say x to the 20. And then you have x cubed plus 2, right? This one right here, this is the highest exponent. And the highest exponent is the degree of the function. That's an important word to know. So quadratic functions, for instance, have a degree of 2. The highest exponent is the x squared. That has an exponent of 2. Linear functions have a degree of 1. There's 1x. The x is only taken to the first power. So the degree is 1. If something is like, for instance, y equals 2, this has a degree of 0. Right? There's no x value, so you can think of it as being 2x to the 0. X to the 0 is equal to 1, no matter what x is. So this has a degree of 0. Something with an x to the 32nd as its highest x value is going to have a degree of 32. The highest exponent is also 1 greater than the highest possible number of maxima and minima a graph can have. That sounds a lot more complicated than it is, but let's think about it this way. If we had y equals 4x, you can imagine the line of that looks something like this. It's probably a little steeper, but it doesn't really matter. This has no local maxima. This has no local minima. It's just a line, right? If we have y equals x squared, this has 1 local minimum. If we have negative x squared, it'd have 1 local maximum, but it never has more than 1. If you do a cubed function, it'll look something like this. This has 1, 2 local minima and maxima. If you do a to the 4th function, it'll look something like this. So it'll have 3. So the degree minus 1 is equal to the greatest possible number of maxima and minima a graph can have. It's also worth keeping in mind that the maxima and minima are always going to be either the same or just one different, right? You can't have like a maxima and then another maxima and then another maxima. They have to switch in order to get new ones. So you have to have an even number of both or close to it. So for example, in the function 4x cubed minus 3x squared plus 2x plus 12, this has a leading coefficient of 4 because the 4 is in front of the x with the highest exponent. It has a degree of 3 because the highest exponent is 3. And it has at most 2 maxima and minima. And that's just because the degree minus 1 is equal to 2. So if we did instead the function, let's do 5x to the 5th plus 3x squared minus 12x. This one has a leading coefficient of 5. This one has a degree of 5. So leading coefficient, that's here. Degree, that's here. And then it has at most 4 maxima slash minima. And that's because it's 5 minus 1. So interestingly, if I did an f of x equals this, x plus 3 minus 16x to the 4th. In this case, it's a little bit tricky because you want to read it left to right and assume that that's the way it's done, but it's not, Remember, these are all talking about the x value with the greatest exponent. And in this case, that's this right here, x to the fourth. So this one has a leading coefficient of -16 because that's the one that's in front of the x value with the greatest exponent. It has a degree of 4 because the exponent itself is 4. And of course, since it has a degree of 4, it's going to have 3 maxima and minima at most. Okay, the last thing we want to talk about in this chapter, there are a couple of other things that we're going to skip over, so don't necessarily go through everything in the chapter, or you might get a little bit confused, or you'll have too much information, which I guess isn't the worst thing. But the last thing we want to talk about is even functions versus odd functions. Obviously, you all know what the words even and odd mean, but when we're talking about functions, they mean slightly different things than what you're used to. So yeah, that's actually literally what I just said. So an even function is a function that contains only even exponents of x. So for instance, 2x to the sixth, that's an even exponent, minus 5x to the fourth, that's an even exponent, minus 3x squared, that's an even exponent. This should not be here. I don't know why it is. That is odd. I thought I took that out. Sorry. So only even exponents here. For reference, because originally I had the -7 in here, that's x to the 0. 0 is neither positive nor neither even nor odd. It's just 0. So you can ignore that one. It shouldn't have had the 7 there. An odd function then is a function that contains only odd exponents of x. Now in this case, you can have x to the 1. So for instance, 2x to the 7th plus 3x to the 5th minus x cubed plus 17x. You can think of this as x to the 1. So 7 is odd, 5 is odd, 3 is odd, and 1 is odd. So this is an odd function. The reason these things are important is actually because of their graphs. So determining whether a function is even, odd, or neither from the formula is simple. If all of the exponents of x are even, the function is even. So if you have x to the 8th minus x to the, whoops, why is that? X to the 8th minus x to the 16th plus x to the 432nd minus x squared. This would be an even function. All of the x's have even exponents, so this is an even function. If all of the exponents of x are odd, then the function is odd. Same idea. We could have, x to the 1 minus x to the 3 plus x to the 5,177 minus x to the 5th. And that's an odd function. All of these are odd. All of the exponents are odd, I should say. If the function contains some even and some odd exponents, then the function is neither. So x cubed plus x squared plus x plus 2. This has an odd exponent right here, an even exponent right here. This would be an odd exponent. This doesn't have an exponent. It's x to the 0. So this one is neither. And remember that the whole number for instance, x, so the whole number that I was talking about, this, like if I have x plus, in this case 4, or if I have like x plus 5, this whole number right here has an effective exponent of 0, which is neither positive nor negative. So basically, if a function has a +7 or a -12 or a +1/3, if it has a number, or that's 1/2, I can't write. If it has a number attached to it that doesn't have an x, it's neither. Because you can think of that as x. Remember, x to the 0 equals 1. So +7 is basically +7x to the 0. And 0 is neither positive nor negative. For now, we're also not going to worry about negative exponents. Your book might, and they work the same way, but it's not something I'm going to talk about. Determining whether or not a function is even, odd, or neither from graphs is a little bit trickier. What we want to do is we want to look for symmetry. If the graph is symmetrical about the origin, or both the x and the y-axis, the function is odd. And I'll show you what this looks like in just a second. If the function is, it should say graph. If the graph is symmetrical about the y-axis only, the function is even. So here's what I mean by that. This graph right here is symmetrical about the y-axis, right? This is the exact same on both sides. When x is -2, so like right here, y is negative, oh geez, that looks like negative 10 or something. And when x is positive 2, it's at the same spot, right? Same with like here when x is 4, x is negative 4. These are at about the same spot. So this is symmetrical about the y-axis. It's not symmetrical about the x-axis, right? If I try to flip that over the x, it's not the same. This one, when we say it's symmetrical about the origin, what we're talking about is if you drew a diagonal line between these two, like this, is it symmetrical? So in this case, if you kind of look at, really what you can do is you can compare, whoops, oh no, it's gonna go out of screen share for a second, sorry. You can compare opposite quadrants for this. It's kind of helpful. So like you'd compare this quadrant over here to this quadrant over here, and then you compare this quadrant to this quadrant. And if they're symmetrical, then you have a function that's the same. But basically, the other way you can think about it is when x is 2, right? Whatever y is, let's say in this case that's, oh, I don't know what this scale is. So 80, I think. It's the worst scale I've ever seen. Okay. When x is negative 2, I think that's there, then y is equal to negative 80. So they're opposite this time. So let's see. For this one's super easy. It's not symmetrical about the y-axis. This weird shape does not really exist on this side. And it's not symmetrical if I drew, whoops, wow, that was terrible. If I drew a diagonal line through it, it's still not going to be symmetrical. So in this case, this one is neither. I guess I should have said on the last one. Oops. This one is even because it's symmetrical about the y-axis. This one is odd because it is symmetrical about the origin. Pretend that goes through the origin. So this one is neither. This one, if we try to look at it about the y-axis, we can really easily pick the point. For instance, 3, when x is 3, or y is 0. When x is negative 3, y is definitely not 0. So it's not symmetrical about the y. And then if we do this, we can pretty clearly see right away that is also not symmetrical. Underneath it is just some weird stuff, and it's not the same on both sides. So this one is also neither. The last note that I want to talk about on these, so obviously these ones are already labeled, right? This one is symmetrical about the y-axis, so it's an even function. This one is symmetrical about this diagonal here. So it's an odd function. But the other thing you can do is plug in values for these. So if it's an even function, g of negative x is equal to g of x. So basically, the y value at negative 2 is going to be the same as the y value at positive 2. The y value at negative 1 is going to be the same at negative 1 or positive 1. The y value at positive 4 is going to be the same at negative 4. I'm making up these numbers, obviously, but the point is, if you go a certain distance to the right and find the y value, it's going to be the same y value if you go the same distance to the left, is the idea for an even function. For an odd function, h of negative x is going to be equal to negative h of x. So if you go, let's say this is 2 to the right, and you have a y value up here. If you go 2 to the left, you're going to have the same y value, but it's going to be flipped. So in this case, it'd be negative, whatever this is, right? And then if we go over here where, like, let's say this is x equals 5, this value is negative. If we go to negative 5 over here, we get the same value, but now it's positive. So basically, the odd functions just kind of flip those two. Identifying these functions is going to be a lot easier when you get more practice and ideally have grid lines. But hopefully this one shouldn't be too terribly difficult for you. And honestly, the stuff that I'm probably going to be asking you about on this is symbolic on tests and things. So I wouldn't spend too much time worrying about the graphs. But if you have any questions, we will have time in class to talk about it. I do want to mention really quick that this is the first section out of 8 that's in this chapter. I'm considering cutting out 2 of them. I haven't decided yet, but that means that homework assignments are going to be shorter, but it's going to be a lot more important to stay caught up. So please try to get caught up, ideally over the weekend if you have to. but try to stay on top of this unit because otherwise you're going to fall a little bit behind, and we want to do this chapter 4 test before Thanksgiving break. But anyway, that's it for this one. I will see you guys tomorrow.